We're a scaleless print team and we are making a research of how does a 3D printer works. With this, we want to follow its principles, but improving 1%, we want to be able to print a real space at 1-to-1 scale. But to be able to do this, let's make a quick review of printing history.
It all started with stone, years before Christ, passing through wood and paper. The rotary press allowed faster printing. Colors appeared on dye sublimation. Scanning was incorporated on the photocopier. Lasers were the new technology in the 70s. The dot-based printing appeared at the same time. Injection made printing massive, and in the 90s, the 3D printer arrived. Since then, its evolution has been slow because it can work on a big scale. This is why we are developing a system capable of 3D printing at any scale possible. Many tried to print simulated space, but we want to present scaleless 3D printing as a way to really accomplish it.
To accomplish our goal, we use different materials, starting with sand. Sand is a mineral element with a maximum diameter of 2 mm apiece. To get this material to create a 3D print, different aggregates were used, with design boxes to maintain and control the sand. By injecting foam into sand, we observed a lack of control over the result. Anyhow, it had a rapid reaction and the prototype was flexible. On the other hand, using a layer-by-layer system, the structure became fragile since the layers weren't integrating with each other. To have a better control of the system, we replaced the foam with white glue by applying it layer by layer. We used the sieve to remove the lumps from the finest particles of the sand, and by using a half-and-half mixture of white glue and water, we had more control in the pixels.
We also used other grains to see if we could obtain a different result. With cat sand and glue, the component broke easily after drying. With rice, the pixel control was better, and so was the resistance, but the result wasn't homogeneous. With beans, the resistance was better if mixing with foam, but on this scale, some resolution was lost. With grape, the glue was in better control, and the resistance was good, so it can be used for bigger resolutions. With gypsum, we were able to control the mixture, creating spaces inside with ice. The resistance was favorable, but the ice was an option for the needed scale.
To improve the system, we started using crystals in the search of transparency. By using a saturated solution of sodium acetate, we found that the crystals form as a cross network of low transparency layers. Once we add sugar replacer to the previous solution, the transparency of the prototype increases by 50%.
Supported or controlling the component with the use of other elements. The perforated tubes were great to direct the glue areas, but the result was too linear. Also, the straws helped to direct the foam. The hose worked to make bigger elements, but they were too fragile. When cotton was used as a pad for the formation of crystals, it dramatically lowered the transparency of the model. With balloons, we were able to create useful spaces, but there wasn't control over their variables.
We proved the different variables of our components. Resistance of beans and foam is impressive. Mixing the foam in equal quantities with the sieved sand makes it fragile and negates all its properties. As the saturated solution of sodium acetate poured in a clean container is touched by the hand, an exothermic reaction begins to form crystals with a color that changes from clear to white very rapidly. If you put one sand before the other, the first takes more space, creating a thin layer below the second. If the two sands are pure at the same time, they contain within its space, creating a division. If you put two sands divided by a wall, when you take that wall off, the division maintains. When the bigger grains are pured before their smaller grains, the big one takes more space, making a big layer under the small ones. If the two types of grains are divided by the wall, when you take that wall off, the division maintains. As our main element is the sand, we tested to see the material variables by dropping the sand at different distances and different times to observe the diameter and height of the pixel that is created and have a greater knowledge of the material and its properties. The higher the sand was dropped, the wider the pixel, but as we came closer to the surface, the pixel was higher.
Using strings to control the formation of space, we managed to create a self-standing structure, but the sand was fragile and the prototype too linear. Sand with CAD sand model was more rigid, but we didn't get as much resolution as wanted, and the piece was still fragile. With two-color sands, we had more control on space formation, but again, it was fragile. Crystal and sand created a mushroom-like model, which accomplished the transparency properties we wanted. Finally, we used gypsum and sand as materials, where we accomplished a pixel control and better resolution on the piece. We tried to find different materials that work as stalactites, hot elements such as wax and silicon that when they have contact with a cold one, automatically create shape. We worked with polyurethane foam to understand how it worked by itself and also with different aggregates. When it worked with ice, we noticed that we can make cavities. Mixing rice, foam, and ice, we can make a rigid mass with cavities. Rice made it very strong, and with the help of straws, we could control it more. The rice helped to be more precise because of its resolution. By mixing with glue, we noticed that it's easier to work with it, that it's slower to make big components. Mixing polyurethane foam with pins make a much more resistant component than with rice, but because of the form of the grain, its resolution is smaller. We tried to focus on the space with sand, using the pixels that the local material conditions gave us. In both ways, leave a layer on one single layer. In the last case, we managed to work without the walls of the box. While working with the foam, we experimented with different combinations of foam mix, using filtered sand, regular sand, and grate. We also tried different combinations of each component of the foam. The white component gives more elasticity, and the black component gives more stiffness. This way, we improved control on how foam falls over the space we had created. In the beginning, we tried different materials, like alum and Epsom salt. We observed that they needed a network to be attached. Cotton proved to be the best absorbing material. By adding alum pieces to sodium acetate, crystals formed a surface of differentiated spaces, creating a needed skeleton. With sodium acetate and Epsom salt, the crystals showed to be very fragile. The crystals formed with sodium acetate and alum powder produced almost the same results as sodium acetate and alum pieces. When a low concentration of sodium liquid is poured, we found that thin crystals are formed within seconds. When searching for transparency, we found that sugar caramel produced a transparent model with highly malleable properties. By adding rice to caramel, the resulting prototype diminished its transparency but increased its spatial resolution. With the projection of an algorithmic variation, the result proved the control we had over space dynamics.
In this system, three main materials are needed: sand, gypsum, and water. We place each one of these on a dispenser bottle. These help us to make it easier to control pixels and resolution while working. There are two ways to produce with this system: a lower and a higher resolution. Lower resolution is accomplished by using a 1-pixel type grid, by previously determining the gypsum and sand pixels. High resolution is based on previous studies of pixel control dependent on height and time of dispensation. In this case, we use graphic algorithm projection on the sand, where the piece was formed with the gypsum. After reviewing and testing all the previous prototypes, we found that the elements and programmatic components that we assumed will remain stable for every case mentioned, collapse in the generation of an innovative, elegant, and functional space, but they set up the principles for the design of a stable programmatic system with differentiated mechanics capable of mutating its character fairly quickly.